You ever have one of those moments? You know, you've got a dozen browser tabs open, music blasting, you're typing away in a document, and you just kind of stop and wonder, how? How is my computer not just throwing its hands up and quitting? Well, today, that's exactly what we're going to get into. We're going to pull back the curtain on the incredible, invisible juggling act your computer is performing every single second.
It all kicks off with something so simple, you probably do it 100 times a day without a second thought. You click an icon. And just like that, poof, a program springs to life. But it's not magic, not really. It's the start of this amazing journey from a boring, lifeless file into something that's active, something that's actually doing stuff. So what's really going on there?
Okay, so the very first thing we have to get our heads around is this transformation. When you double-click that icon, your operating system takes a static thing called a program and turns it into a living, breathing thing called a process. And trust me, that distinction is everything.
And the difference? Well, it's like night and day. A program, that's just a file sitting on your hard drive. It's passive. Think of it like a recipe in a cookbook. It has all the instructions, sure, but it's not actually making dinner. A process, on the other hand, is the act of cooking. It's that program loaded into the computer's memory, running those instructions and actually making things happen.
So once this program becomes a process, what does it actually look like, inside the computer's memory? It's not just some big messy blob of code. Nope, it's a super organized structure with a few key parts, and each one has a very specific job to do.
All right, so when the process gets loaded up, it's divided into these four main sections you see here: the text, the data, the heap, and the stack. Let's do a quick tour of what each one does, starting from the bottom and working our way up.
First up, we've got the text section. This is basically the brains of the operation. It's the actual machine code, the step-by-step instructions that the CPU is going to read and follow. This is the core recipe we were talking about, the real logic of the app.
Right above that is the data section. Now, if the text section is the recipe's instructions, think of this as the list of ingredients you know you'll need before you even start cooking. This part holds all the global variables, all the pieces of information the program needs right from the get-go.
Now this is where things get interesting. We have the heap. This is a super flexible area of memory that grows upwards while the program is running. You ever notice your web browser getting slower and slower the more tabs you open? Yeah, that's often the heap at work, because each new tab is asking for another chunk of memory. It's the space for all the stuff the program doesn't know it needs until it's already run.
And finally, growing down from the top, we have the stack. This is a very neat and tidy, last-in, first-out space that's all about managing functions. It's like a stack of plates. You put one on top, you take one off the top. It keeps track of temporary data, and most importantly, it remembers where to go back to when a function is done. It's the process's short-term memory, basically.
Okay, so now we know what a process is made of. But here comes the real puzzle. Your computer probably only has a handful of CPU cores, right? But you can have dozens, even hundreds of processes running. How in the world does it manage to pay attention to all of them?
I mean, really think about that for a second. It feels like your browser, your music, and your chat app are all running perfectly in parallel, but they're not. Your CPU is actually a master illusionist, and it has this incredibly clever trick up its sleeve. And the secret to that trick is a special little ID card.
And here it is, the hero of our story, the process control block, or PCB for short. Every single process in the system has one of these. It's like a process's passport, its driver's license, and its entire life story all rolled into one. It contains absolutely everything the operating system needs to know about that process.
And it is jam-packed with vital stats. It knows if the process is currently running or waiting for something. It stores the CPU's current scratch pad in things called registers. But the most critical piece of info, the real superstar here, is the program counter. It's like a bookmark that points to the exact next instruction the process needs to run. The PCB is basically a perfect snapshot that can freeze a process in time.
All right, so with the PCB as our key, we can finally unlock the real secret to multitasking. It's a lightning-fast move called the context switch.
So check this out. On the left, a process, we'll call it P0, is running along, doing its thing. Then, suddenly, bam, an interrupt happens. Maybe you moved your mouse, or a bit of data came in from the network. The operating system instantly swoops in. It saves the entire current state of P0 into its PCB. Then, it looks at its to-do list and decides, okay, process P1, you're up. It loads the state of P1 from its PCB, and just like that, P1 picks up running exactly where it left off last time.
So let's just run that back. An interrupt happens, the OS saves the current context, it reloads a new context from another process's PCB, and the new process takes over. This swap happens hundreds, maybe even thousands of times every single second. It's so ridiculously fast that to us slow humans, it feels like everything is happening all at once.
Now, here's the catch. During that tiny fraction of a second when the switch is happening, the computer isn't actually doing any useful work for your apps. It's pure administrative time, overhead. But without this tiny bit of overhead, the entire illusion of multitasking would just fall apart. It's the price of admission for the smooth, responsive experience we all expect.
And to make this all as efficient as possible, the OS is incredibly smart. It knows that not all processes are created equal. You've got I/O-bound processes, like a word processor that spends most of its time just sitting there, waiting for you to type. It only needs short, little bursts of CPU time. And then you have CPU-bound processes, like a video editor that's rendering a huge file. That thing needs long, uninterrupted chunks of time to just crunch numbers. The OS knows the difference and schedules them intelligently to keep the whole system feeling snappy.
The operating system also has something called a long-term scheduler, which basically acts like a bouncer at a really popular nightclub. Its whole job is to control how many processes get let into memory to compete for the CPU's attention at any one time. This keeps the system from getting way too crowded and slowing down to a crawl for everybody inside.
So, the next time you're effortlessly gliding between a dozen different apps, just take a second to remember this invisible dance that's going on. From that simple program file becoming a living process, to the PCB saving its state, to that lightning-fast context switch, it's this beautifully complex ballet that truly makes our digital lives possible.
This whole ballet of processes, it really defines modern computing. But think about this. We're moving towards a world with billions of connected devices. Our phones, our cars, our smart toasters, all of them running processes. What does this dance look like when it's happening not just on your laptop, but at the scale of trillions across the globe? Now that is something to think about.